All right, Coulombs Law is an equation for calculating force between two charges. So second semester is going to be all things pertaining to charge. And whenever it applies, I'm going to relate it back to mass, because the way things work with masses is very similar with how it works with charges. And this is a good example. All right, so what is Coulomb's law all about? It's basically an equation for finding the force between two charges. So here's the equation right here. Oops. The equation is F equals K Q1 Q2 over R squared. Now, what does this look remarkably similar to? If you think back to first semester, what did we learn about all masses? If you have two masses, what do all masses in the universe do? They attract, right? The world's greatest pickup line, Newton's law of gravitation. All objects in the universe are attracted to each other. So we learned in first semester, if you have M1 right here and M2 right here, what will these two forces do? I'm sorry, what will these two masses do? Attract each other. And what was the equation for finding the force between those masses? G M1 M2 over R squared. And remember, R is from center to center. That was important with masses, right? Like if it was a planet, from center to center. What's big G? The gravitational constant, which you don't have to memorize. That'll always be given, whether you're on the multiple choice part of the AP or the free response. Big G is always given, but I'll just put it down here. Big G is equal to 6.673 times 10 to the negative 11 Newton meter squared over kilogram squared. Okay? Now, with charges, it's very, very, very similar with a couple key differences. Like, for example, do charges always attract each other? Charges can either attract or repel. So when do charges attract each other? If they're opposite, one's plus and the other one's minus, they're going to attract. When do charges repel each other? When they're the same. So that's a key difference, right? Because with masses, are there different types of masses, or is there just mass? There's mass. Masses will always attract. Charges can either attract or repel, depending upon whether you have opposite charges or like charges. Okay? But notice that these two equations are basically the same equation. Do you guys see that? Gm1 m2 over r squared, k q1 q2 over r squared. It's basically the same exact equation. Now, what is q? So q is kind of new for this, well, for the whole class. Previously, what was q? We used q in the past as being the symbol for heat. Q was heat, but not in this chapter. In this chapter, the symbol q refers to charge. Q is charge, and charge has a unit. Hey man, m is mass. What's the unit for mass? Kilograms. What's the unit for charge? Coulomb. The unit for charge, it's right here in the law, Coulomb. Right here. Coulomb. The unit for charge is the Coulomb. Now there's two very important charges that you have to know. And it'll be given, like when you're on the AP exam, if you happen to forget what this charge is, you can look it up. But the two very important charges are the charge of a proton and the charge of an electron. And even if you took AP chemistry, you've probably never learned this. Like in chemistry, what do you call the charge of a proton? Positive. The charge of an electron? Negative. Well, positive what and negative what? Well, there's an actual value to the charge of a proton and the charge of an electron. And it's this number here. The charge of a proton is positive 1.6 times 10 to the negative 19 coulombs, and the charge of an electron is the exact same value, but just negative, right? Now this number here, the 1.6 times 10 to the negative 19, that number is referred to as an elementary charge. Did I spell is that right? Yeah. That's referred to as an elementary charge. Now, why would we call that an elementary charge? Because that is what does elementary mean? Basic, fundamental. The reason we call this an elementary charge is because it is the building block of all charge values. So, for example, what's the smallest possible charge you could have after 0? I mean, I guess 0 would be the smallest charge. 0 would be the smallest. What's the next biggest charge after 0 that you could have? So it goes like this. 0 is the smallest charge, 0 coulombs. What comes after 0? 1.6 times 10 to the negative 19 coulombs. What would be the next biggest charge after that? 3.2 times 10 to the negative 19 coulombs. What's the next biggest charge after that? 4.8 times 10 to the negative 19 coulombs. And then after that, boy, this is really stretching my math abilities here. 4.8, 6.4 times 10 to the negative 19 coulombs. So charge comes in these bundles of 1.6 times 10 to the negative 19 coulombs. Does that make sense? In other words, we say that charge, you'll sometimes see this. Charge is quantized, meaning that it comes in specific quantities. You can't be like, could I have like half of that? I don't want that full. Could I have half that? What's the answer? No. Right? Like my sister is the queen of special ordering at restaurants. I don't know if that relates here or not. So anyway, moving on. This number is an elementary charge. It's the charge of a proton, charge of an electron. Charge comes in those bundles. You should just be aware of that. All right, now, what is K? So K, guess what K is? It's a constant. Do you have to memorize it? Nope, it'll be given. K will always be given. It's referred to as Coulomb's constant, and it's 9 times 10 to the 9th Newton meter squared over Coulomb squared. So look how similar it is. So look at the unit here. Newton meter squared over Coulomb squared. What was the gravitational constant? Newton meter squared over kilogram squared. So first semester was all things mass. So see here in the constant, kilograms. Second semester is all things charge, which is Coulomb. Okay. Any questions with this? It's a pretty straightforward topic. Now, a few things I want to mention. So let's get rid of our gravity one here. So look, if you have a big charge, so we'll say a big positive charge, and a little negative charge. So we'll call this guy Q1 and this guy will be Q2. Is there a force on charge 1 exerted by charge 2? Yeah, because we know that, opposites attract. What is the negative charge doing to the positive charge? Pulling or pushing? Pulling. So we'll label this F12. What does F12 mean? The force on 1 by 2. Okay, and then what is the positive charge doing to the negative charge? Also pulling. So that would be F21. Now look, are these forces the same in value or different? Charge 1 is big, charge 2 is small. Same force or different force? They are the same, right? We talked about this when we did masses. Basically, what does Newton's third law say? Newton's third law says that every force has a what? Equal and opposite reaction force. So look, if the negative charge exerts a force on the positive charge, that's this force. So what's the positive charge doing to the negative charge? Exerting a force back. Every force has an equal and opposite force. So even though we have a big charge and a little charge, the force between them is equal, right? Okay, what else? All right, two very common metric prefixes that you're going to see in this chapter. Micro and nano. Okay, so you're going to see problems where they're like, boom, here's a charge. It's equal to 5 nanocoulombs. Are you going to take this and plug it into Coulombs Law as is? What is nano? So the prefix nano is 10 to the what? Negative 9. The way I first memorized that, this n right here, nano, n is for what? 9. That's how I first memorized it. Nano is 10 to the negative 9. And then what is micro? Micro is this cursive, it's mu. It's 10 to the negative 6. Okay? So 5 nanocoulombs, what are you going to do? You're going to go 5 times 10 to the negative 9. Put it in coulombs. When you plug into this equation right here, these Q's have to be what? Coulombs. So what if they tell you, like, all right, Q is equal to 3 microcoulombs. What do you have to do? 3 times 10 to the negative 6. Micro and nano are used a bunch. Okay? All right, then the final thing I want to mention, final thing is notice that in the what's one difference between these equations? What do you notice about the Q's? What do you notice about the Q's in the Coulomb equation here? They're absolute valued. Now, kids always ask about that. They're like, why are you absolute valuing the Q's? Well, what does it mean to absolute value? It means don't worry about what? The minus. Don't worry about minuses. When you're plugging into the Coulombs Law equation, don't worry about plus or minus. Everything gets plugged in as a positive. Now, guys, what's the reason for this? It's real simple. What does plus and minus tell us in physics? Direction. Plus and minus tells us to the left, to the right, up, down. It tells us the direction. Will this equation tell you the direction? Absolutely not. It will not tell you the direction. And let me give you an example. Ready? We have two charges. I'm not going to tell you which one's which. Okay? So we have a charge here and a charge here. One of them will be charge 1. So let's say that charge 1 is positive 5 nanocoulombs. Charge 2 is negative 3 nanocoulombs. Okay, which way is the force on charge 1? To the left, to the right, up, down? Well, can you answer that question? No. See, what I'm saying is like, look, could you just take these values right here, you know, and obviously you got to convert it to Coulomb, but could you just go plug in, and be like, oh, the force is to the right? How do you figure out the direction of a force when you're dealing with charges? Not from the equation. You're going to figure it out from how? By looking at the diagram. You have to look at the situation. So let's say I told you that this guy was charge 1 and this guy is charge 2. Could you now figure out which way the forces will be? Yeah. So let's see. Charge 1 is plus. Charge 2 is minus. So now that you know which one's which, okay, which way is the force on charge 1? To the right. Which way is the force on charge 2? To the left. Now you can figure it out. The equation is not going to tell you which way the force is. And that's why it's absolute valued. Okay? All right, so let's look at an example. Okay, so this is a good Coulombs Law problem. So we have 3 charges, okay, and they're arranged on an XY axis. And these are 2 different questions here. A and B are completely separate. So we have 3 charges. Notice that they're given in nanocoulombs. So you got to take that. You got to go, you know, for this right here, that would be 5 times 10 to the negative 9 coulombs. Put it in coulombs. So we have 3 charges arranged as shown. Find the net force on, so for A, we're focusing on this guy. And then for question B, we're going to focus on this guy. Okay? All right, so let's do part A. I'm going to start you on this. Okay? So focusing on the 5 nanocoulomb charge. How many forces are acting on this 5 nanocoulomb charge? 2. So this guy's plus, this guy's plus, this guy's plus, this guy's minus. All right, so what is the 6 nanocoulomb doing to the 5 nanocoulomb? Pushing or pulling? Pushing. So we're going to have a force to the left, right? There's going to be a force to the left. What is the 3 nanocoulomb force charge doing to the 5 nanocoulomb charge? Pushing or pulling? Pulling. So we have a force pointing down like that. So the first thing you got to do here is find out what these forces are. What's this force and what's that force? Now, how are you going to find out what that force is? Yo.
I have a question. Why is it going left?
Because, let me back up here. So the question is, why is that first force to the left? Because this guy's positive and that guy's positive. Like charges repel, right? 2 positive charges are going to repel each other, right? And then, by the way, you know, if you look at the 6 nanocoulomb charge, there's going to be a force to the right. You know, these forces are equal and opposite, but which charge are we focusing on? Are we focusing on the 6 nanocoulomb? No, we're focusing on the 5, so we can kind of just, you know, we don't have to do a diagram for the 6 nanocoulomb charge. All right, so what you got to do, so we've identified the direction of the force. Now what do we have to do? We got to find out, well, what's this force and what's that force? How do we find out what those forces are? F equals K Q1 Q2 over R squared. And you have the distances. Now, once you know what those forces are, once you figured out each of those forces, then what do you have to do? It becomes a vector problem. What do you do to those 2 forces once you know what they are? You put them what? Tip to tail, and then the answer that you're looking for is the hypotenuse. That make sense? Yo. K is 9 times 10 to the 9th. Newton meter squared over Coulomb squared. Okay, real quick, because I'm going to let you guys try this. I'm pretty much done for the day, but let me just explain why B is a little trickier. Now, why would question B be trickier? Because now we're focusing on this guy, on the 3 nanocoulomb charge. Okay, so what are the forces on the 3 nanocoulomb charge? Well, what's the 6 nanocoulomb doing to the 3 nanocoulomb? Attracting it like that. Uh-oh, there's the tricky right there. What's the tricky? It's at a what? This vector right here is at an angle, meaning it's not perfectly x and it's not perfectly y. Okay? What is the 5 nanocoulomb charge doing? Attracting. So that one's not bad at all. That one's fine. Okay, so we got these 2 forces. What you're going to have to do is you're going to have to solve for an angle, right? Because you have a triangle here. You got a triangle. So you're going to have to solve for the angle. You're going to have to figure out what's the distance from here to here. You're going to need that distance right there, right? So it's a little trickier. Part B is definitely more work than part A, okay? So you're going to break this guy, you know, let me switch to the red pen here. You're going to break this guy into X component and Y component. It becomes a vector problem. Look, but is it difficult because of chapter 15? No. What makes this situation tricky? Way back, it's vectors. You learned this back at the start of chapter 3, I think. It goes way back to like September, October. All right, so try this. And you know what? I'm pretty sure I have a video solution for this problem. So you can if you're not getting the answers, the answers are given up here. If you're not getting these answers, you can check my video solution.